Okay, so good afternoon, everyone. I'm Yoshinobu Kawahara, team leader of Structured Learning Team, Riken AIP Center. Thank you for joining this AIP Open Seminar. So first, I'd like to notice, I'd like to read some important notices about this seminar. So first, production is prohibited, and second, reproducing all or any part of the contents is prohibited without the author's permission. Third, this seminar will be recorded and the video will be available on the Riken AIP website later. And if you have any questions or comments, please scroll to the bottom of the page and click the Q&A tab. You can put questions or comments in the box. Okay, so again, I'm Yoshinobu Kawahara, team leader of Structured Learning Team. So today's AIP Open Seminar is going to be by our team. So I hope you enjoy this. Okay, so let's get started. So today's seminar is it consists of two parts. The first part, I'll be overviewing a structured learning team, and second part, we will have three research talks. The first one by myself, the second one by Fujii-san, and the third one by Umetani-san. So I'd like to start the first part. Okay, so this is the first time for us to talk at the AIP Open Seminar. So I'd like to introduce a bit about our team. So this is our members, the member of this team. So okay, I am Yoshinobu Kawahara, and there are three postdoctoral researchers, Israel, Macias, and Hatano-san, and one technical staff, Nishimura-san. And we have three visiting researchers, Umetani-san from Osaka University, and Fujii-san from Nagoya University. He was previously a research scientist at this team, and Takeshi-san from some university in Switzerland. I forgot the name, and he was also previously a postdoctoral researcher of this team. And Konishi-san from Kyushu University. He is a project assistant professor at Kyushu University. And two research part-timers, Kojima-kun and Inoue-kun. They are students of this at my laboratory in Kyushu University. My team leader position is a concurrent post, and I am also working at Kyushu University as a faculty. So our working place is located at the Ito campus of Kyushu University in Fukuoka. This campus is quite new and very large. In fact, the largest in Japan as a single campus. So and actually, it's very beautiful. The environment is very beautiful, so I like it. So anyway, so this is our desk space, and this is discussion space. And the name of structured learning teams come from the following concept. Okay, so I'd like to explain about that briefly. So when we solve some problems using based on machine learning, we often have prior knowledge about the problem or mechanism that is expected to generate data. And as you know, such information is very useful to improve the machine learning, the accuracy, the performance of machine learning in accuracy, and also make models more interpretable. Also, often useful to accelerate the computations involved uh, by using structures, by using such knowledge. So we have so in this team, one of our challenges is to develop methodologies to uh, to use such prior knowledge, especially on structures among uh, variables or the generic mechanisms, both in modeling and computations. For example, so combinatorial structures over variables are structures that we often encounter when we solve machine learning problems, such as which includes the graph structures, hierarchical structures, or group structures over variables. And it is known that such structures can be represented in a general manner using some modular functions, which is discrete functions with convexity. And so based on such relations between convexity in discrete functions and also combinate structures over variables, we have been we have developed formulations for a variety of learning problems, including regularized learning and Bayes learning, and also developed practical optimization methods for those formulations, and apply those to related machine learning problems or applications. And then one of the another one focus of this team is the case of dynamics as a structures, uh, so where we may you deal with time series or spatial temporal data, or more generally, so when we deal with dynamics as a data generating mechanisms, the prior knowledge is described as usually described as mathematical models, using mathematical models such as differential equations or some discrete time systems. And in this team, we try to extract information about dynamics from data, and connect those to the knowledge about the dynamics, which is usually described as dynamic systems. And so and yes, as a formulation and develop such formulation to connect the knowledge and data is extracted informations, and for the purpose of understanding of dynamics in phenomena, some dynamic phenomena or behaviors of which are interested in natural sciences, or to use those in prediction or simulations of complex dynamics behavior, and or to use those to analyze learning mechanisms in machine learning models, such as neural networks. Okay, so so although this is a very brief, but I like to move on to the next part. So is there any question or comments so far? So maybe no question or comments. So I'd like to move on to the second part. Okay. Okay, so let's move on to the research talks. So first talk is by myself, and I'd like to speak about operator theoretic data analysis for dynamic systems, which is a kind of approach that's under this concept. And the second talks will be by Fuji-san. The title is Data-Driven Analysis for Multi-Agent Trajectory in Team Sports. And the third one is by Metani-san, and the title is Exploiting Variable Associations to Configure Efficient Local Search Algorithms in Large-Scale Binary Integer Programs. So I'd like to start my talk. Okay, so I'd like to start with the background. So as you know, when we when we handle dynamics in a broad sense, there are two approaches basically. So in the forward approach, or mathematical modeling approach, we develop some mathematical models based on some knowledge, uh, or knowledge, or knowledge, and uh, which are often described as differential equations, ODE, ordinary differential equations, partial differential equations, or discrete time systems. And and based on such model, we try to analyze or predict the behavior of dynamics. On the other hand, data-driven approach in data-driven approach, we use data, and based on and using data, we solve some sort of inverse problem to extract some information about the dynamics, or to model the to approximate dynamics that is expected to generate data for the purpose of understanding of data generating mechanisms, or the purpose of prediction or simulation, and so on. So as you can imagine easily, so machine learning is a key framework for this for under this approach. In fact, such problem, so the problem of this extracting some property of dynamics has attracted much attention in various fields. So, in fact, you can find many papers in scientific journals with high impact, such as Nature, Science, and PNAS, and also papers in uh, machine learning top conferences such as NeurIPS and iClear. However, this problem is still challenging, and because there are many difficulties so in principle, and of course, there are many reasons. But the one of the main reasons of the difficulty is nonlinearity, of course, because it is in principle difficult to deal with nonlinear dynamic systems in a general manner, like the case of linear case, both from the mathematical practical perspectives, and also this the dynamics of interest in recent in in recent studies, both in scientific and engineering fields. The dynamics is not easy to describe explicitly using mathematical models. So so of course, a data-driven approach becomes more and more important in under this because of these reasons. Operator theoretic method, which is a basis of operator theoretic data analysis, the topic of today's talk, it has attracted much attention as one of the prominent approaches to this problem. Okay, so so to explain about the operator theoretic method, I'd like to explain first Koopman operator, which is one of the most important concept in operator theoretic method. So as you know, dynamic systems, which I said before, so which is usually described as differential equations or discrete time systems, describes a trajectory in state space, which is which is a space which is usually finite dimensional space, and where system is defined. And the Koopman operator gives a kind of lifted representation of dynamic as this nonlinear. So usually this f, so the dynamic system is depends on the map f, which gives a match f, which is usually nonlinear. And the Koopman operator usually gives a kind of lifted representation of nonlinear dynamic uh, systems like this. And so where the Koopman operator described, so is denoted by k here. So in this representation, so we first consider some function g defined in state space, which is often called observable or observation function. And the Koopman operator gives the evolution of this function, this, the evolution of the observable. and defined by this behind that as in this equation. Okay, as you can see, uh, so here, so bar phi, so bar phi is a flow. Flow is a map, um, given from the system. So uh, so flow maps the state to the next time step. Okay, so a Coupon operator is defined by as in this form, and as you can see, by applying Coupon operator to observable, uh, you know, actually this is a new function, and this function, after by applying Coupon operator to G, uh, is if we input some state to this function, then this function gives you know uh, um, the observation functions over the state at the next time steps. So anyway, so this operator gives evolution of functions instead of state directly. And as you know, so function is can be regarded as infinite dimensional vectors in a yeah in a mathematical sense. So this gives a and also we can easily show that this operator is linear. So Coupon operator can so gives a linear and infinite dimensional representation of nonlinear and finite dimensional uh, systems. And this interpretation is quite useful from several viewpoints. And one important interpretation of this, one important thing is that this, representation is closely connected to the understanding of complex dynamic phenomena as nonlinear oscillations embedded in high dimensional space. So often known as phase. So yeah, okay. So, often discussed in nonlinear science. So as you know, many natural dynamic process around us, such as uh, brain, heart, our heartbeats, and the chemical and physical process. We often observe uh, some rhythms or periodic behaviors, and such behaviors can be often described as oscillators in embedded in high dimensional space we observe. And Koopman analysis, the operator, so analysis with Koopman operator is closely related to this understanding of complex phenomena, which I explain later briefly. Okay, so and then one advantage of using coupon operator is that, as I said before, the operator, because the operator is linear, we can calculate Eigen decomposition. So Eigen decomposition. So here that lambda is eigenvalue and psi is eigenfunctions. And using eigenvalue and eigenfunctions of coupon operator, now we can we can give our model representation of the evolution of observables. Here, bold G is you know set of observation functions which appeared in the previous slide. And so anyway, so the evolution of observable can be described using eigenvalue and eigenfunctions in this form. And here, please note that k, which actually gives temporal information. The k appears only here in this part, the power as a power of uh, over eigenvalue. And please note that lambda is complex value. So which means that the eigenvalue has a phase and amplitude. So this means that in each component, so anyway, so the evolution of the observable can be decomposed into the components where you know, so and each component has unique frequency and decay rates, uh, only depending only on the eigenvalue. So that is frequency is determined by the phase of lambda, and also decay rate determined by absolute value of lambda. And the other part, this part can be regarded as weights over dimensions of G. And this description, this representation is closely related to the understanding of complex dynamics as oscillators, which I talked in the previous slide. So this is a brief explanation about that. So assume we have some that behavioral dynamics is embedded in high dimensional space. So and in the field of phase reduction, which is the part of nonlinear science, they in formal manner they develop map from this space to another space where this oscillation is described. So typically one-dimensional space where this, where uh, uh, the dynamics described as stationary angle rates with stationary angle rates, and actually, in general, so in many cases, so this map can be obtained using as eigenfunctions of coupon operators. For example, this map, so the map to one-dimensional phase equation can be given as angle of eigenfunctions of the first of the that correspond to eigenvalue, uh, which is the most close to the to one. Okay, and okay. So anyway, so you based so anyway, so such maps can be given as a function of as an eigenfunction of coupon operator. Also, another important things based so related to coupon operator is that so we have many sophisticated estimation method such as dynamic mode decomposition, and dynamic mode decomposition is a popular numerical method to approximate coupon operator, and has been discussed much in various fields, which appears originally in fluid dynamics field. Okay, so and this is a numerical example of dynamic mode decomposition. So where we apply, so this is an example of the application of dynamic mode decomposition to fluid dynamics, the flow after the cylinder. And the below figures, the bottom figures shows the result by DMD, dynamic mode decomposition, the eigenvalues, and the other part, so eigen function, the part for yes, the eigenfunctions, the weights over dimensions. So in the case, the data is observation is uh, given at each grid in this space. Okay, so yes, and in this case, as you can see, there are uh, so we have 13 eigenvalues in this case, but because these, but and essentially you know uh, these eigenvalues are equivalent because, for example, the third eigenvalue is given by multiplying the second eigenvalues, and this eigenvalue twice, 3 times, and so on. So this means that this anyway. So this system has basically two modes, and the first one is actually the value is one with no imaginary parts, which means that this is constant dynamics, and this is a corresponding spatial pattern. And so these modes correspond to the flow around the cylinder, shear layer. And this part correspond to the wake, the behavior of wake. And this is quite useful because to understand the dynamics, this so complex looking dynamics of flow, because now we can describe this phenomena using only one, you know, one oscillating dynamics with constant dynamics. So we can understand this complex phenomena like the movement like this in one dimension. One dimension means that the angle, the space of angle. So like this. Okay. So yeah. So very becomes very easier to understand the dynamics. Okay. So now we have a question. Um, is it possible for KMD to decompose any complex system into single Frankish time series? Are there any exception or constraints? Okay, so this decomposition is, so we have a question. So the question is again, so is it possible for KMD to decompose any complex system into single frequency time series? Are there any exceptions or constraints? Okay, so yeah, of course there is a constraint. So although I did not explain, so here we assume that the operator, so operator, linear operator, generally has spectrum of three kinds: point spectrum and three resolvents. So point spectrum and continuous spectrum and I don't know how to say in English, Joyo spectrum in Japanese, Joyo in Japanese. But here, but to obtain this this decomposition, we assume that K has only point spectrum. Yes. So, but in general, dynamics has other spectrum also. But if we try to uh, so estimate this decomposition using data, as explain later, of course we can just estimate points. I mean, the eigenvalue. So we can obtain only eigenvalues as only points. So other spectra usually cannot be caught. Um, so yes. So exactly to say, if we like to have this decomposition, we need to assume operator has only a point escape spectra. But it's in the perspective of estimation. So in other words, so we uh, assume that we can approximate sufficiently well only using point spectrum. Okay. Okay. So I answered the questions. Okay. And okay. So and DMD, another good point of DMD, this kind of approach is can be implemented very easily. This is four procedures for DMD. The called exact dynamic mode decomposition, which is one of the most popular procedures for DMD. And so I omitted. So if we have a sequence of vectors, we we basically need to calculate twice of Eigen decomposition, so singular value decomposition and the Eigen decomposition of matrices. And then we have approximate decomposition like in this one. And as you can see, this is quite easy to implement. And the previous result, this result is obtained by this procedures. And in more generally, dynamic mode decomposition can be described in this form. So assume we have given finite samples, which may be a pair of samples, consecutive pairs of which is as supposed to be generated right um, in this form, and also given by a set finite number of linearly independent functions, which may be obtained by applying PCA and so on. And then we first solve this kind of least square problem, which is actually multivariate regression problem. And then the finite approximation of Coupon operator is given by like this, with the matrix, so the solution to this least square problems. And so this is a general description of DMD called extended DMD, and is shown to converge to the to a Coupon operator under some assumptions if it exists. And we apply this kind of approach. So because of the time limit, I don't go into the detail, but I apply this approach, kind of approaches, for example, to the analysis of human behavior, like locomotion, and also video analysis. And also you can find many application of this sort of analysis in various fields, including physics, such as fluid dynamics and high energy fields like plasma, and also in engineering fields, and also other fields such as brain data analysis, human behavior analysis, and economics, and infection propagation analysis, and so on, and also robotics, and so on. Okay. And another concept, which another important concept related to operator theoretical method is the conjugate of Coupon operator, called transfer operator, or called Perron-Froobès operator or Markov operator. So as I said before, Coupon operator gives describe the evolution of observation function, observable function. Instead, transfer operator gives evolution of distributions, such as probability distributions. And these are actually conjugate. Uh, in this case, not conjugate, but usually, so in general, we can consider conjugate. So for the if we have a Coupon operator in some mathematical setting, then we can define the corresponding uh, uh, transfer operator, uh, yeah, in general. So anyway, so these are so such through such conjugacy between Coupon operator and the transfer operator, we can analyze also behavior of distributions. For example, if we use kernel, reproduction kernel, in this case, the transfer operator is defined in RKHS, determined by reproduced kernel. And so here, as you know, that we can calculate inner product by evaluating kernel functions. So which means that we can calculate Eigen decomposition of this operator if we have data. So and in this case, if for example, if we map some distribution, a sequence of distribution into RKHS through, for example, economy embedding and so on, then we can analyze, evolution of distributions by calculating Eigen decomposition of operators in this space. And also, so using the conjugacy between the transfer operator and the Coupon operator, where we can analyze the the I don't know dynamics, the origin dynamics of underlying um, un, um, underlying behind data. So this is some numerical example for generated the data, the application to data generated by double jive. The double jive is described in this equation, and which has two attracted fields like this. So which means that if we start from here, then that point is attracted left hand side, and if you start and some start here, then the point is attracted in the right hand side and so on. Okay, and if we calculate the uh, eigenvalues of this that eigenvalues of this operator in using data from this system. Um, so this is a result for by applying such approaches. And if we look at the eigenvalue uh, of value 1 with no imaginary part, then the corresponding eigenfunction is becomes like this. And which means that these so as I said, I explained it before. So the attracted part have high values, and because these eigenvalues correspond to to correspond to distributions after so that I don't know how to say uh, after time passed infinitely. So which means anyway. So this dynamics converge to these distributions. If we start uniformly from uniformly from this field, and okay. So anyway, so this eigenvalues and eigenfunction can capture such dynamics of distributions. Also, this kind of approach, this kind of formulation is useful for predictions. So as you know, principal component analysis capture the information with respect to property in as a static property of data. So that information about distributions. So on the other hand, the dynamic mode decomposition, which also can be regarded as matrix decompositions. So because just twice of the Eigen decomposition. So the resulting decomposition can be regarding procedure can be regarded as matrix decomposition, and the so into the decomposition into two parts, and the one of those the one that correspond to eigenvalues, which actually capture the temporal patterns, and the other parts actually capture the spatial pattern, where each sort of so in other words, how each dimension share the corresponding temporal patterns. Okay, so if we'd like to use these features, so these extracted features in predictions, we can, for example, construct some the kernel or measure to comparison uh, by based on the subspace spanned by the spatial patterns. Okay, because the of course if we apply DMD to different sequential data, we have a different temporal pattern, so we cannot compare the spatial pattern directly just by calculating in a product between matrices. So we need to consider a subspace spanned by such columns of these matrices. So and if we and by evaluating the for example angles between subspaces, we can compare the spatial patterns extracted by DMD. And once we obtain such such measure for comparison, we can use those to in various machine learning models such as SVM, KNN, and neural networks. For example, so we apply this to brain-computer interface. So where the problem is to predict the behavior of some guy, some human, some guy. So only using brain signals. And so in this application, so we have this is an example of DMD feature. The features extracted by special patterns extracted by DMD and also the FFT. And as you can see, so in this case we have three behaviors: grasping, pinching, and opening. And as you can see, DMD features capture different special patterns according to the different behaviors. And in fact, we could achieve you know uh, a big improvement from the conventional FFT approach in this context using based on this approach. And also this kind of topic can be generalized to more general dynamics. So theoretically, so this is so I don't go into the detail. If you like, if you are interested in this, please look at this paper. But if we can, so using the representation with linear operators, in this case, Perron-Fluvis operator, transfer operators in RKHS, we can compare general dynamic system, nonlinear and non-stable systems um, by systems. We define as some this kind of angles, which is actually reproducing kernel, and which generalize existing distances for time series models, such as armor, distance based on armor, and so on, and so on. So and so on. Okay, and also this kind of concept is related to stability, and so recently the stability the learning with stability has attracted much attention, and in fact this is useful. So the understanding of Kupa operator uh, uh, related to stability is useful in this context. So so actually, so eigenfunction of Kupa operator generates the so-called stability, which is often discussed in control theory, to general global case, which is called isostable, and can define Laplace function, more general Laplace function. And usually in the context of control theory, the stability is defined with respect to equilibrium point, but this stability can be defined on in general stable manifold. Okay, so and uh, so for example, so this is a research by Manek and Code in New Lips last year, 2 years ago. And so in this paper, so Manek, they develop learning method to learn dynamics and Laplace function simultaneously to learn stable dynamics. So so here they they consider kind of projection of learned dynamics into the stable one through the property of Laplace functions. And if we and we can generalize this to but their method is based on the stability with respect to equilibrium points. But we can generalize this to more general case, the stable stability over general manifold, smooth manifold, uh, uh, yeah, using based on the based on the idea of Kuppner operators, the stability, global stability. And this is very useful to predict complex phenomena for long time prediction. So for example, so the fluid dynamics case, this is some numerical example. We can predict this complex phenomena. So for so um, for longer time predictions. Okay. This is because, as I said, I explained before, so this complex behavior has, can be described well with oscillators embedded in high dimensional space. So if we, learn dynamics based on such stability, we can use such, a dynamics, a property of dynamics in the prediction. And maybe I don't have time. So there are many, but this type of approach has still have many technical problems, and that should be addressed in the futures. I omit maybe I don't have time, but the one of the one important problem is the selection of observable. I did not explain before, but the selection of G, so which is functions which that define the Kuppler operator, is affect the accuracy of this to this kind of analysis. And this is an example. And so I cannot go into detail, but so in this case, so this system, so this is a correct selection of the observable, and this system has imaginary, so a spectrum on the imaginary axis. So wrong selection of observable gives wrong, estimations. So which means that anyway, so selection of G is affects the accuracy of the analysis. And so for this to overcome this issue, we can, for example, use neural networks. So which means that we estimate observable and also perform DMD simultaneous on just using data. So so this is some so for example, in this paper, which may be the first paper discuss about this issue. So we construct laws that correspond to DMD and also the observables. And this G is a kind is so this G actually encode the data into the space that define a Kuppler operator, and we decode again to the signal, so observable signal. And so this corresponds to G, observable facts. So we learn observable and also DMD simultaneously. This, okay. And also this can be done in end-to-end manner because Eigen decomposition can be, so in the previous one, we after estimating observable, we need to apply DMD um, over the vectors, uh, transformed vectors. But we can do the calculation of Eigen decomposition, so DMD, in end-to-end manner also, because Eigen decomposition can be done using auto differentiation of Eigen decomposition. And so in this case, we can have eigenvalues in the learning. So in okay, so learning, so we can you know um, obtain more precise Kuppler decompositions, which is also useful also in prediction. Sorry, I don't have time, so I don't go into detail. If you are interested in this, please go into this archive paper. Okay, so and the summary. So okay, so because the non mathematical models, so dynamic systems, which is usually nonlinear. So so because this is usually difficult to handle because of nonlinearity, so we analyze dynamics that is supposed to generate data through representation with operators such as Kuppler operator through the linearity of the operator. And so based on such approach, we connect extracted information from data to to knowledge about dynamics, which is actually so dynamic systems. So and today I talked about about the method to extract dynamics, model decomposition, model representation of dynamics, and also the use of those representation in prediction of complex dynamics. So we are also working on the use of this kind of approach to the analysis of learning, machine learning models. Maybe next AIP Open Seminar, maybe we can talk about this. Okay. Okay, so this is summary. So again, so please contact me if you are interested in collaboration with us. Okay, thank you. Okay, so if you have any questions or comments. Okay, so I have one comment. So I have another comment, another question. So is it possible to analyze the algorithm of transformers for NLP and deep reinforcement learning in a structured way? Actually, so um, transformer is also neural networks, and as you know, so neural networks can be regarded as dynamic system. So we may deal with such the dynamics using based on this kind of representation with operators. Yes, and yes, I don't know the papers. No existing paper about that. And also, of course, reinforcement learning. Yes. Also, in the as you know, in reinforcement learning, we learn, the environment and policy simultaneously, and of course, the environment in the dynamics, is a dynamic system, and so we can, you know, use operator theoretic approach to model this kind of in reinforcement learning also. Yes. Okay, so is there any other questions? Okay, so the second talk is going to be by Fuji-san. So the title is Data-Driven Analysis for Multi-Agent Trajectory in Team Sports. So Fuji-san, can you start?
Okay, thank you for the introduction. And I am Keisuke Fuji, and here I will talk about in this title. And so recently I uploaded the preprint paper here in this topic. So if you are interested in this topic, please see this paper. And this is today's talk outline. And first, I will introduce my biography and the general background of multi-agent trajectory analysis. And the main topic is about the theory-based data-driven approaches. And here I will introduce two studies. And the first is physically interpretable classification method called graph DMD. And the second is method to generate trajectory using policy modeling with partial observation and mechanical constraints. And then the first is the introduction of my biography. And when I was a student, I was interested in human motor control during the interactive situations. And in the first postdoc, I was studying in team sport science as a data analysis. And from the 2017, I was a research scientist in this team and start to investigate the machine learning methods for team sports analysis or multi-agent trajectory analysis. And now I am an assistant professor in Nagoya University and continue to study machine learning methods for multi-agent trajectory analysis. And next is a general background in multi-agent trajectories. In general, many researchers have investigated the behaviors of pedestrians walking, human walking, and animal group behavior, like this picture. But my main focus is on more complex behavior, like children's play or athletes' ball game behaviors. In such a topic, we aim to reveal the principle behind the measured data, but it is often difficult to model them due to higher order interaction. The higher order interaction includes some complex cognitive and complex movement characteristics. Next is motivation in the application side. Why do we model multi-agent behaviors? For example, in team sports. In the team sports, player position data can be recently measured in actual games, such as in this video. However, team tactics are analyzed based on watching videos by using such editing software and counting the play frequency and so on. And this is because team tactics are difficult to model, predict, and control in the current technologies. If we automated this procedure by introducing such a measurement system, it is expected to reduce the workload on experts and promote understandings of audience and beginners. The next is general problem setting using the theory-based and data-driven approaches for the modeling. The left is a theory-based or equation-based or deductive approach in which the researchers manually create thefunctions such as social force model and simulate the trajectories and evaluate or test their hypothesis. And this approach is easily understands the mechanism, but it is sometimes difficult to model the complex behavior. In contrast, data-driven approach or equation-free or inductive approach, we use the data, complex data, and machine learning or statistical methods. We can predict future motions or validate the models in the various metrics. This approach is easily model the complex behavior, but it is sometimes difficult to understand the mechanism. And then there is a gap between the two approaches. Our main motivation is to analyze the real-world agents, so the data-driven method to extract the principle, in this case, for example, dynamics, will be needed. More precisely, I can show a diagram for categories of approaches for the analysis. The higher means the approach based on the theory or experiments, and the lower means approach based on the machine learning. The right is a data-driven approach, and the left is a model-driven approach. In conventional approach, using the data, we create the handcrafted features and they perform data analysis. And in contrast, we sometimes construct a mathematical model to represent the phenomena. And there is a gap between the two approaches. Using the machine learning-based approach, we can construct a data-driven model. But our main focus is on theory-based data-driven modeling, in which for the understanding of the phenomena and between the gap, bridging the gap among the first, second, or third approach for the understanding. Another research direction is learning-based for the modeling, but in the virtual space, but this topic is skipped in this talk. So I introduced the third in general data-driven approaches in the team sport analysis. And this approach can extract the global spatial temporal dynamics in actual games. For example, using the motion data, the feature or representation is learned and perform classification or regression, and finally obtain the level prediction or motion prediction. Uh, in this approach, many methods have recently been proposed, but in this talk, I skipped this to introduce the approaches. So please see this survey paper. And for example, we previously proposed motion classification and score prediction methods in basketball data. And we performed we compute the DMD, which is introduced by Carl Hassan's previous talk, and perform calculating the kernel or similarity, and perform classification, and finally obtain the label or score prediction. This approach requires less specific knowledge and obtains global and general properties. And again, so although many methods have been proposed, but I want to know what kinds of methods are needed for the understanding of sports or multi-agent behaviors. Then we need theory-based data-driven modeling. And to understand the behaviors, bridging theory-based and data-driven approaches is needed. The next question is, what kinds of nonlinear data-driven model will enable a better quantitative understanding? Such discussion is already exists in data-driven model that contribute to the sciences. In this paper, in addition to predict the phenomena, explaining this and being served as a starting point for establishment of new theories are required for the scientific understanding. In multi-agent sports behaviors, for example, a method to extract the mathematical structures from the perspective of physical sciences, and a method to model the components of multi-agent systems and generating plausible movements from the perspective of behavioral sciences will enable a better scientific understanding. Then today, I will talk about the two specific studies and following this topic. And then, next topic is about the study of physically interpretable classification called graph DMD. This paper is published in scientific reports, and the paper and the codes can be accessed. And this slide is a continuation from Professor Carhar's talk. And we used DMD here as a physically interpretable feature extraction method. This is a basic DMD algorithm called exact DMD algorithm. The input is a data matrix, data dimension, and data time, and Y is a time-shifted matrix. And the output is DMD eigenvalue lambda or frequency omega, and initial value, and this is a temporal dynamics, and it's special coefficients psi called DMD modes. The basic idea is numerically Eigen decomposition of transition matrix F, but for stable computation, in this algorithm, we perform SVD and project F onto space spanned by U and perform Eigen decomposition and obtain eigenvalue and DMD modes. Then I introduce the background of graph DMD. We previously, again, we applied DMD in reproducing kernel Hilbert space to time-varying collective motion, like basketball trajectories, and developed classification method using spectral kernel. But there are two problems in this work. The one is the kernel method is highly expensive, but it is difficult to interpret the modes due to the decomposition of in future spaces. The second is that the motion can be represented as network dynamics, like this, but that did not reflect the graph structures. Then we propose a graph DMD for interpretable classification using the decomposed modes. This slide is related work in network science. In general, complex systems can be modeled as networks using graphs, including nodes and edges in many scientific fields. For example, sociology, epidemiology, neuroscience, physics, chemistry, and so on. And most of these works focused on the network property and performing classification, prediction, and control. However, these methods mostly did not extract a dynamical property of network dynamics. And then we propose graph DMD. In this algorithm, we formulate such network dynamics as a graph dynamical system and observe the space. And we utilize the adjacency matrix structures for the algorithm. These structures indicate the order 3 tensor, nodes by time. And this should not be decomposed as a matrix. Then graph DMD algorithm is introduced. The input is the data tensor and time-shifted data tensor. And we first performed a decomposition of capital X after the matrixing of data tensor mathcal X by tensor train decomposition. And this form equation is very similar to SPD, but it is completely different because it reflects the tensor structures. Especially the M is worked as a projected matrix in the direction that reflects the data property. Then we compute pseudo inverse of capital X like this. And in particular, we propose a more straightforward formulation compared with previous work using the pseudo inverse of n. Then we compute approximation of Coupon operator or transition matrix or tensor f hat like this. And in the following procedure is very similar to the basic DMD. Perform Eigen Decomposition of lambda and finally obtain the DMD modes per phi like this. Then we can perform physically and semantically interpretable classification for the basketball real-world multi-agent data. And this is a basketball trajectories with some relationship. And the input is sequences of sorted adjacencies matrices denoted as A, and based on the distance between the two agents. The value becomes 0.5 when the distance is 1.5 meters, which is a meaningful distance in the basketball. And then we perform graph DMD, which decompose into semantically interpretable spatial modes and physically interpretable temporal modes. But the basketball trajectory is usually time-varying dynamics, so we use sliding windows of 2 seconds interval. Then we obtain features, for example, simply vectorized features or graph features. Then finally perform the classifications. The next is the comparison of classification performance with conventional methods. The task one is we have two tasks in basketball classification, and task one is one. The first is team defense classification task, zone defense or person-to-person defense. The second task is team offense classification with or without cooperative play. We have three proposed methods, classification methods. One is simple vectorized features, and the second is graph Laplacian, graph features, and the last is also graph using graph structures, graph convolution network, using the graph DMD modes. The baseline, we have four baselines. The first is a simple basic DMD and spectrum, and the second is our previous kernel DMD and the spectral kernel. And the third is the simple hand graphitative feature, and the fourth is spatial temporal graph combination network as an end-to-end method. In both tasks, team defense and team offense tasks, our proposed methods were validated by better performance than the baselines. The methods can interpret the extracted features. For example, in team offense, this is an example of attacks with cooperation here. And this is an example of attack without cooperation. Among the nearest attackers, so there was a stronger spectra among the nearest attackers here. So these nearest attackers can strongly couple like oscillator-like behaviors. In the team defense, similarly, this is a zone defense example, and this is a person-to-person defense example. In the zone defense, we observed the stronger spectra among the nearest defenders, like this. In such a way, this method can automatically extract global and interpretable features in the collective dynamics. Then the next topic is about the method to generate trajectory using the policy modeling with partial observation and mechanical constraints. And this is uploaded as a preprint paper here, and the codes can be accessed here. As a background, in general data-driven agent-based modeling, this approach can generate trajectory in actual games by such as time series modeling, reinforcement learning, and imitation learning. In this approach, using the training data, the multi-agent model is learned, and the model can predict the future motions by multi-agent model and the initial conditions in text data. There are many techniques which have been proposed recently in neural network approach, such as recurrent neural network or graph neural network, GAN, and other deep generative models. This approach can perform long-term prediction using actual data. However, the conventional data-driven models have three problems. Firstly, these methods assume the agents fully utilize the environmental information. The second is that the optimized communication or centralized control is assumed in this work. The third is the methods ignore the mechanical constraints of players' bodies. However, real-world agents usually selects the player's importance based on the partial observation, and the agents behave in a decentralized manner, and the agents reflect physical and biomechanical constraints. For example, in the real-world agents have shows smooth movements rather than the jumping in the long run. And our contribution of this work is to construct the data-driven models satisfying such requirements. And finally, in the experiments, we validated it by visualizing the generating plausible behaviors. This is model components and overview. And mainly, we have the model have 4 components: the partial observation and macro goal, local policy, and mechanical constraints. In the partial observation module, the model learned the binary vector whose information is utilized from the input states and output the observation O. Second, macro goal is used as a weak supervision. This is squared. These squares for performing long-term prediction. This is learning by the pre-trained model, and in the main training procedure, we utilize as a weak supervision, and in a decentralized manner in this work. Local policy as an input using observation as an input and output the actions, we utilize variational RNN. And the final mechanical constraints includes 2 penalties. One is a physical penalty for inconsistency among the position, velocity, and acceleration. And the second is a biomechanical penalty for changing in acceleration to realize the smoothness of the agent's behavior. And before the detailed methods, we first introduce data and tasks. And we use 2 data sets. One is soccer data sets, include 45 games in Europe leagues obtained from here. And the second is a basketball data set, including 100 games in NBA obtained from here. As a prediction task, the model predicts the player's trajectory in a defensive team, and the model predicted 6-second trajectories from the 2-second trajectories. The model input is all players' position, velocity, and acceleration, and both position and velocity. But note that model is partially constructed as a partial observation. The output is each defender's velocity and acceleration, and the reason of the selection of this variable is described in this paper. And next is model details and results about third components, decentralized local policy. The baseline is a variational RNN, which added the stochastic hidden state Z to the famous recurrent neural network. And we used hierarchical VRNN with the macro goals, which is a decentralized version of previous work, which is the blue part is a macro goal and near to the components of VRNN. And we evaluated our methods using the root mean square error of 6-second prediction. And our model is validated the better prediction performance in the basketball data and soccer data, position, velocity, and acceleration compared with baseline methods. And next is details and results about fourth components, mechanical constraints. We designed the constraint losses or penalties for optimizing neural networks. And note that, again, our model directly predict velocity and acceleration and indirectly predicted positions. We propose three penalties here. And the first is the difference in distributions or KL divergence between the direct prediction, A hat, and indirect prediction, A tilde, which is computed by the difference between the using the direct prediction of velocities. The second is the difference between indirect prediction distribution, A tilde, position T, and the ground truth, A position, and by negative log likelihood. The third is the difference between the direct prediction distribution, A hat, ATT, ATTT, ACCT, and the next true acceleration, ACCT plus 1. Based on, and this is IEA is based on the minimum jerk principle for the smooth movements. The results have shown that in this graph, lower is better, and compared with the baseline VLNN, our methods show a smaller difference between these two variables and distributions in both basketball and soccer datasets. Finally, we show the partial observation results. In average value, observation coefficients or number of observation show it's 4.42 in basketball datasets and 8.014 in soccer datasets. Then we show example of prediction and counterfactual prediction. And the ground truth in such the defender is a color, and gray is a attacker, and then black is a ball. Such show complex trajectories. And note that there is no true observation. This is a predicted results, and show a complex trajectory similar to the ground truth. And the advantage of these methods is to visualize the observation of the players. For example, this is a observation of the defender number one, and observed many people, and defender number one took a balanced position between the attacker number one and others' movements, our other agents. Next advantage of this method is to perform counterfactual prediction by manipulating the observation. For example, only one person. For example, if the defender number one sees only this attacker number one, this defender number one follows this attacker number one, like ball game beginners. This is intuitive for basketball coaches and players. Finally, I will show the conclusion. And the motivation in this talk is to bridging the theory-based and data-driven approaches to understand multi-agent sports behaviors. Then I introduced two studies, and for detail, see my survey paper. And thank you for the listening. And we have two questions, and I will answer in this order. And the first question is that the data is usually observed with noise. And are there any methods to evaluate the uncertainty of results in the statistical sense? This is a very general question, and also treated. So this question is maybe about the. So I have introduce two methods, but so in both cases, formulation as a probabilistic model is possible. So the question is yes, and the answer for the question is yes, but by using the probabilistic model. So so if you so for example, DMD approach is also formulated as a probabilistic model as explained by the Kawahara-san's talk. And the latter model is formulated as to output the distribution or probability of the probabilistic model. So this is the answer is yes. And the second question is that so second question is that is your graph method equivalent? So rotation permutation equivalent, or so for example, rotation of players gives the same results. This is a very good question in one of the important problem in the multi-agent trajectory analysis. And in our case, so we tackle this problem by in the first method. In the first method, I treated this problem using taking a nearest player to the ball, and then the order is almost determined in a unique manner. In this method, we use the sorted. We sorted the order by nearest player to the ball. The second method, I did not explain the methods, but I used as a pre-processing method. We use the permutation methods used in many methods by the hidden Markov model of to permutate the order of the players. So please see this paper. The appendix in this paper describe the methods precisely, and the code is also can be accessed. And do you have any other questions? If no, my presentation is finished. Will be finished.
Okay, Fuji-san, thank you very much.
Thank you very much.
Very much. Okay, so yeah, we'd like to move on to the next talk. Okay, thank you, Fuji-san, again. Okay, so Metai-san, could you share the slide? Okay, so the next talk is by Metai-san, and the title is Exploiting Variable Associations to Configure Efficient Local Search Algorithms in Large-Scale Binary Integer Programs. So yeah, Metai-san, please start.
Thank you very much. So, and in this talk, I'll talk about the local search algorithm for integer programs. Okay, so let me first start my introduction. So apart from the machine learning, so my major interest is mathematical optimization, especially for combinatorial optimization. And so my recent research topic is to develop heuristic algorithm for large-scale combinatorial optimization problems, and especially for the automatic algorithm configuration for general purpose solver. And so I also interested in the real applications, and develop the optimization models and algorithms for these applications. And so the latest news, the first news is I have published an introductory textbook on mathematical optimization written in Japan. The name is Shikkari Manabu Surisaitika in Japanese. The second news is the proposed algorithm in this talk has been released in the latest version of the software package called Numerical Optimizer. This is developed by an entity Data Mathematical Systems Incorporation. Okay, and let's start the two types of approaches for hard combinatory optimization problem. So as you know, so the many real applications and can be formulated as a combinatory optimization problem. But so we also know the most of combinatory optimization and is very hard, as known as the NP-hard problem. So for this and the problems, so the first approach is to develop general purpose algorithms. In this approach, we first formulate real problems into general models and such as a mixed integer program and constraint satisfaction problems. This approach has a wide availability, but hard to achieve high performance. The second approach is specially tailored algorithms. So many researchers interested in the second approach. In this approach, we first extract the special features of individual problems to improve the performance of the algorithm. This approach in general attains the high performance, but hard to achieve wide availability. And generally, it is very difficult to balances and between the high performance and the wide availability. But this is just the main objective of my research. That is, and my theme is how to achieve both high performance and wide availability. In this talk, we consider the binary integer program. The binary integer program is a general model and having many real-world applications, and such as crew scheduling, big routing, facility locations, and so on. In the literature, based on linear programming techniques and many exact and heuristic algorithms have been developed. So many large-scale BIP instances still remains, and due to a large gap between the lower and upper bounds of the optimal values. Okay, next, and for this situation, so let me talk about my approach overview. The BIP is a general purpose optimization problem. So having quite few good features to improve efficiency of algorithms. So this is true and about the problem formulation. But this is I believe this is not true about the instance data, and that is and we consider extracting good features from the instance to be solved in this and in the proposed algorithm to improve efficiency of the local search algorithm. So, and we now introduce a simple data mining approach for reducing the search space of local search algorithm for BIP. And next, I will talk about the meta-heuristics, the summary. The meta-heuristics can be considered as a collection of ideas on designing heuristic algorithms for optimization problems. The ideas of meta-heuristics gives us a kind of systematic view by incorporating them into greedy and local search algorithms. So, however, we often need to extract the special features of individual performance problems to achieve high performance in practice. So that is a crucial issues to develop meta-heuristics, especially for general purpose meta-heuristics. So I think so it is very important to develop I know the general purpose and meta-heuristics, but it is very hard because of the general purpose problem has no special features. So this is the outline of the proposed algorithm. The BIP is, of course, the general purpose optimization model. So now, and we developed the local search-based algorithm for the BIP. And the main component of the proposed algorithm is as follows. The first component is exploiting variable associations to reduce the search space. So this is the main contribution. The second one is efficient incremental evaluation. The third is adaptive control of penalty weights. And next, I will talk about the local search algorithms. Local search is the basic component of the metaheuristics. It starts from an initial solution X and repeat replacing X with a better solution X prime in its neighborhood. And until no better solution is finds in neighborhood. And in local search algorithms, so searching the larger neighborhood increases the chance to find a better solution. That is the larger neighborhood make improvement of the local search algorithm. However, but the larger neighborhoods and to search larger neighborhood, it is very time consuming. So when designing the local search algorithm, we often feel crucial to balances between the performance and search efficiency. So for the BIP and the binary integer program is very difficult, even the problem, and only to find a feasible solution is NP complete. So the proposed algorithm allows the excess and shortage of each constraint and then introduce the penalty functions with weights WI plus and WI minus. So these and penalty weights will be adaptively controlled in the search and explained later. So, and for VIP, we consider the K-flip neighborhood for VIP. So the K-flip means that at most K variables and can be flipped in the current solution. The for-flip operation includes representative operations and in many combinatory optimization. And let me see the two figures. And for example, in the assignment type problems, we often exchange assignment between two agents. That can be expressed as the subset of for-flip and neighborhood. So, however, the for-flip neighborhood is too large to search efficiently in large-scale instances. So the issue is how to define the search and large neighborhood. So apart from the meta heuristics, and let me see about the MIP solvers techniques. So MIP instances often include the characteristic part of special constraint, and extracting them may improve the performance of MIP solvers. I'm sorry, so MIP means that the mixed integer program. So, however, extracting characteristic parts of constraint matrix is basically very hard. And for example, and extracting a maximum totally unimodular matrix is NP hard. So we have taken another approach for local search algorithms. So we focuses on the variable associations. So this is the first main component. So the proposed algorithm find the promising pairs of variables in the two-flip neighborhood from the instance to be solved for reducing the search space. So that is, so we keep pairs of variables xj1 and j2 having similar columns in the constraint matrix. As shown in the left figures, and the each columns corresponding to the variables and the xj1 and xj2. So we check the inner product of the pairs of columns, and so we found the similar columns and the pairs of similar columns, and stores this relationship as the k-nearest neighbor graph. When searching the local search algorithm, so the search the candidate solutions only checking only for edges in the k-nearest neighbor graph. So, and to implement k-nearest neighbor graph, so we introduce neighbor list implementation. So for each variable xj1, we enumerate variables xj2 with the top 5m largest and the inner product into the j1's rows of the neighbor list. So, however, constructing the whole neighbor list is still very time consuming for large scale instances. So we adapt the lazy generation of the neighbor list. So that is starting from empty list, and we incrementally compute the corresponding rows of the neighbor list when flipping variable j1 in the two-flip neighborhood search. So furthermore, so using k-nearest neighbor graphs, we extend the two-flip neighborhood search to search space to search a set of promising solutions in larger neighborhoods. That is, we developed the four-flip neighborhood search for an improving solution by flipping four variables alternately along the four passes or four cycles in the k-nearest neighbor graph. Okay, let's proceed to the second component, the incremental evaluations. So naive implementation of the local search algorithm requires to scan the constraint matrix to compute the evaluation function for each evaluating the neighbor solution. So it's very time consuming. So, and we utilize the auxiliary data. So we compute the increase of the evaluation function and in constant time when flipping variables. And the auxiliary data are updated only when updating the current solution. So that is important. So the feature that is let me see the footnote. So the number of the evaluating neighbors is much larger than the number of updating the current solution. This means that of course the updating the auxiliary data takes a certain and computational effort, but the number of updating the auxiliary data is very few. Okay, so let's proceed the third component, adaptive control of penalty weight. So we incorporate an adaptive control of penalty weights WI plus and WI minus to escape poor locally optimal solutions and intensify the search around the boundary of feasible region. So substantially, and if the current the evaluation function value of the current solution is larger than the incumbent values, and we decrease the penalty weights and uniformly. So that is a difference that is different from the standard penalty function method. So otherwise, so we increase them the following formula. And this formula means that the increase penalty weight with respect to the violations of each constraint. So based on the proposed algorithm, we have tested the proposed algorithm for benchmark instances, mainly the set covering problem and set partitioning problem. This table shows the summary of the tested set covering problems. So we note that and these instances include the very large scale instances up to 1 million variables. The next one and is the summary of the set part and the instances of set partitioning problem. In the set partitioning problem, so the largest instances is up to the 2.5 and the million variables. So we first and compare the several variations of the proposed algorithm. That is, so the without neighbor list, without incremental evaluation, without for flip neighborhood. So this is the summary of computation result for set covering problem. So we observed and that 15 to 20 times faster than the naive implementations. And of course, that made in the improvement of for performance. This slides and this table shows the computation results for set partitioning problem. And especially so we note that for the hard set partitioning problems, the four flip neighborhood works very effectively. So we also compared and the proposed algorithm with the recent solvers. And for example, so several general purpose solvers like the Cplex, Groby, and so on. And so for the set covering problem, we compared one and especially tailored the sort algorithms. So compared to the general purpose algorithms, the proposed algorithm attained a better result for the set covering instances, and also and comparable result to the specially tailored algorithms. And this is the computation result for set partitioning problem. So the set partition problem is so the very difficult problem because so only to find a feasible solution. So but so the proposed algorithm attains a better results than the and general purpose solvers. Okay, so finally, and I conclude remarks. So in this talk, we introduce a simple data mining approach to reduce the search space of local search algorithm by extracting the instances to be solved. So especially we construct the parts of the K nearest neighbor graph on demand, and that identifies the promising pairs of the flipping variables in the two flip neighborhood search. I think so that we consider the meta heuristics in the view of data mining techniques and for developing general purpose solvers. And that is all. And thank you very much for attention.
Thank you, Metani-san. So is there any question from the audience? If you have, please write it in Q&A or raise your hand. So Metani-san, can I have one question?
Yes.
So so not today. So today in today's talk, you use closeness of variable columns, right? Based on k-nearest graph.
Yes.
Is it any property that is that might be useful in this BIP, such as, for example, diversity or something like that? I don't know. So any structures except for rather than other than closeness.
I see. So the research I focuses on the closeness.
Sorry, I just wonder.
Yes, yes. So that is yes, yeah. It may be important so that to capture and to extract the diversity of the yes, yes, yes of the solution in the search space. Okay, so and basically in the meta heuristics is so the two types of and strategy maybe is important. That is the intensify and so the diversity. And the local search is based on the intensification approaches. On the other hand, so for example, multi-stat and strategy, for example, so the genetic algorithms and particles from optimization. So the focus is on the diversity of the solutions. In this sense, we can extend the local search algorithms, so combining or introducing such kind of diversity approaches. And so some of diversity approaches introduces, and for example, the metrics and also diversification and the statistical diversification. Yes, in this sense, we can extend for such a direction.
Okay, thank you. So yeah, I have this question because yesterday there is a seminar by about determinant point process, which leads to diversity. And actually, it was used in successfully used in stochastic optimization, stochastic gradient descent for neural nets. So I just wonder. So yeah, okay. Thank you.
Yeah. So I think that's a very important point. So the traditionally, so in the meta-heuristic area, so introduces heuristic approaches mainly. So, but in the future, I recommend it may be better to introduce statistical method to make diversity of the search, I think.
Okay, thank you. That'll be very interesting. Okay, thank you. So, is there any other question? Maybe no. Okay. Okay, so thank you again, Metai-san. Yes, thank you for your interesting talk. Okay, so now we had 3 talks, and so if you have, we can accept if you have questions about any of our talk. Maybe no, we will finish. Okay, so thank you for joining us. Okay, so now today's we want to finish today's seminar, but we will have this series of seminars. So schedule like this. So please join. So again to this open seminar. Okay. Okay. So thank you very much for joining us, and thank you, Midai-san and Fuji-san. Okay. So okay, see you again sometime somewhere. Okay. Bye bye.